Welcome to the Reinforcement Learning series. In this first chapter, we'll explore the fundamentals of reinforcement learning, a paradigm where agents learn to make decisions by interacting with their environment. Unlike supervised learning, where we have labeled examples, RL agents must discover optimal behaviors through trial and error, receiving rewards or penalties based on their actions. So what exactly is reinforcement learning? At its core, RL is about an agent interacting with an environment in a continuous loop. The agent observes a state, takes an action, and receives a reward along with a new state. This is fundamentally different from supervised learning, where we have pre-labeled training data. In RL, the agent must explore to find what works. Real-world applications include game-playing AI, robotics control, and financial trading systems. The mathematical foundation of RL is the Markov decision process, or MDP. An MDP is defined by 5 elements: S, the set of possible states; A, the set of available actions; P, the transition probability function; R, the reward function; and gamma, the discount factor. The Markov property states that the future depends only on the current state, not the history. This simplification makes the problem tractable while still capturing many real-world scenarios. The Bellman equation is the cornerstone of RL algorithms. It expresses a recursive relationship. The value of a state equals the immediate reward plus the discounted value of future states. This elegant equation tells us that we can compute optimal values by considering one-step look-ahead and bootstrapping from estimated future values. The discount factor gamma determines how much we value immediate versus future rewards. Value iteration is our first algorithm for solving MDPs. We start with arbitrary value estimates and repeatedly apply the Bellman update until convergence. Each iteration improves our value estimates by considering one-step look-ahead. The algorithm is guaranteed to converge to the optimal values. Notice how the values propagate from the goal state backward through the grid as iterations progress. Policy iteration takes a different approach with 2 alternating phases. First, policy evaluation. We compute the value function for the current policy. Second, policy improvement. We update the policy to be greedy with respect to the computed values. This process repeats until the policy no longer changes. While each iteration is more expensive than value iteration, policy iteration typically converges in fewer iterations. One of the central challenges in RL is the exploration-exploitation trade-off. Should the agent exploit what it knows works well, or explore to potentially find something better? Epsilon greedy is the simplest approach. With probability epsilon, take a random action. UCB, or upper confidence bound, adds an exploration bonus based on uncertainty. Softmax exploration uses a temperature parameter to control randomness. The optimal strategy depends on the specific problem. 2 fundamental approaches for learning values are Monte Carlo and temporal difference methods. Monte Carlo waits until the end of an episode and uses the actual cumulative return. TD learning, in contrast, updates after each step using bootstrapped estimates. MC is unbiased but has high variance. TD has some bias from bootstrapping but lower variance. TD methods can also learn online without waiting for episode completion. Let's see these concepts in action with a grid world example. Our agent, shown as a robot, must navigate from start to the goal while avoiding traps. Each cell has a value representing the expected return from that state. The arrows show the optimal policy, which direction to move from each cell. Notice how values decrease as we move away from the goal, and the trap has a very negative value. Let's recap what we've learned. RL enables learning through environment interaction. MDPs provide the formal mathematical framework. The Bellman equation enables recursive value computation. Value iteration and policy iteration are fundamental algorithms for finding optimal solutions. And balancing exploration with exploitation is crucial for effective learning. In the next chapter, we'll dive into Q-learning and SARSA, practical algorithms that learn without knowing the environment model.